Okay, now we are going to consider type 2 error. Type 2 error is the opposite of type 1 error. Remember, type 1 error happens when you reject a correct hypothesis. But type 2 error happens when you do not reject a wrong hypothesis, right? So the point here is type 2 error happens when you don't reject, right? And we can use the same critical values we used before. And remember, we are interested in non-rejection. Non-rejection happens when the sample average lies between these critical values. So if the sample average is close enough to your hypothesis, 81, then you will not reject the null hypothesis, so type 2 error can happen. But another thing you have to think about here is, now you have to assume that the null hypothesis is wrong. Null hypothesis is wrong. That means mu is not 81 anymore. We believe that mu is 81, but actually it was not. So we need another value, which is kind of arbitrary value, another value you would like to calculate the type 2 error. So here I will consider 82. So I will think about what the case where aspirin was actually larger than it had to be, 82 milligrams, but still, so say it's 1 milligram larger than it had to be, but you may fail to detect that error. You may fail to detect that problem. So what we will consider what's that probability. And then we can formulate the probability of type 2 error in this way. So again, probability type 2 error happens when x bar, sample average, lies between those two critical values. But remember, we are going to use the assumption that the truth is actually 82, right? Actually, it doesn't need to be 82, but just as an example, we will use 82. Later, I'll show you what happens when it is different. Okay? And then, again, the idea is the same. We are going to use the center limit theorem, and then we are going to standardize, and then we are going to use Excel to calculate the probability. So first, center limit theorem. Now, standard deviation is the same as before. Standard deviation is the measurement error, which is still 5 milligram, and sample size is still 100, so it's not a problem. But the problem is, the center of the sampling distribution is now 82. We assume 82 because we assumed 81 is wrong. So it is not centered around 81 anymore. And then, we learned the sampling distribution. Then we need to standardize the sampling distribution to standard normal distribution. So this is the probability we are calculating, and we learned this distribution. And standardize. Remember, again, we use 82, which is the difference from type 1 error. So in type 1 error, we used 81 because the null hypothesis was true. But now we are using 82, which is an alternative to the null hypothesis, right? And the standardization is not different except for the number. But as a result, the resulting numbers are not symmetric anymore because 82 is used. And you know how to calculate this probability. Probability of a standard normal distribution on a certain interval We learned how to do that in chapter 6, right? So it shows that type 2 error probability is 48%, right? So 1 milligram difference is really hard to detect. You fail to detect it with 48%. So, and as I said, the probability is calculated based on the assumption that 82 is truth. But you could think about 83, 84, 85, or 81.1, 81.2, right? Any number different from 81 implies the null hypothesis is wrong. But intuition is clear. Like if you assumed, say, we only considered 1 milligram difference. But if the difference was, say, 10 milligrams, then I would expect this probability would be much smaller. So if the difference was larger, then it is much easier to detect that difference. But in this case, 1 milligram is too small, so we have this high type 2 error probability. If, like, on the other hand, if the difference was even smaller, say 0.1 milligram, then it would be very, very difficult to detect it. So the type 2 error probability would be like 90%, for example. So this number does affect the type 2 error, which is very intuitive. And also, we need to understand the relationship between type 2 error and the significance level alpha. So again, the intuition goes like this. Type 2 error happens when you do not reject. When you don't reject, you may have a type 2 error. But if alpha is higher, if the higher alpha is, the higher the significance level is, the more rejection you are going to make. That means more rejections imply fewer type 2 errors, because type 2 error happens when you don't reject. So higher alpha means lower type 2 error. It's trade-off, right? So here exactly I said the same thing. Type 2 error happens when it's not rejected, and when alpha is higher, more rejections, so fewer type 2 errors. So alpha and type 2 error goes the opposite. Okay, now let's compare type 1 error and type 2 error. Type 1 error is often considered more important and more serious problem, right? Because the null hypothesis is always favored. That's the idea of presumption of innocence. We value we think it, so let me just read it. It is better that 10 guilty persons escape than that one innocent suffer. So we would like to minimize the type 1 error in our legal system. That results in the presumption of innocence. And in statistics, same thing happens, and so we would like to put type 1 error under our control. So we think type 1 error is a more serious problem, so we would like to control that, so we choose the significance level. So at the beginning of hypothesis testing, you declare how much type 1 error you can allow. So that's how we control the type 1 error. So say, for example, I am willing to sacrifice 1%. 1% type 1 error would be okay. Or if you don't worry too much about type 1 error, you can say 10%. 10% type 1 error is acceptable to me. So in that way, we are by construction, type 1 error is under our control, but type 2 error can happen with a higher percentage, like you see here, right? Type 2 error probability could be quite high depending on the truth. Okay, now it's your turn to do the algebra, the exercise. So now I change the dose to 325 milligrams, a larger dose, right? Same brand. We are going to consider same structure with different number, and I'll still use the same scale. So measurement error has a standard deviation of 5, and sample size the same, and significance level the same, 5%, right? We are going to do these 4 things. First, we will find critical values, and then type 1 error and type 2 error, and then we will see what happens when alpha changes. First, calculate the critical values we are going to use for the error probabilities. Try this. Okay, so the formulas are the same, but the center should be the new number, new hypothesis. You have to use the new hypothesis to calculate the critical value, the center of the critical values. So 325 and the same thing, because we use these numbers, right? I believe this process is not that difficult. Okay, so that means now still the margin of error is actually the same, because we are using the same significance level, same standard deviation, same sample size. So only the center changes, but the margin of error is still plus minus 0.98 milligrams. So using these critical values, what is the type 1 error probability? So you may use the critical values here. Okay, the answer is 5%. You don't need any algebra. I said that the significance level significance level is the type 1 error probability. So without any calculation, you can just say 5%, right? Okay, always equals. Okay, now then, it's time to calculate the type 2 error probability. So first, I'm going to ask you this one. What probability do we need to calculate? We already know the critical values, but which side of the critical values do we have to calculate? And remember, type 2 error probability is the probability of not rejecting the null hypothesis. So think about that and guess what's the probability we are calculating. Okay, so this kind of question is the most important part, because if you don't know what probability you have to calculate, then there is no hope. You cannot do anything. So the answer is A, because it happens, we are calculating probability of not rejecting the null. Not rejecting the null means the sample average lies between the critical values. So that's the reason why you calculate option A. And so type 2 error probability is this guy. We calculated the critical values, so simply we can use the numbers. Okay, now I'm going to stop the video here. Now you calculate the type 2 error probability. I already gave you this, so you know how to do it. First, you find the central limit theorem normal distribution for x bar, and then standardize the probability, and then use Excel or a calculator to find that probability. Okay. When you finish the algebra, start the next video. See you later.